assignments for today are to finish this, we'll do them in math. Finish this handout of examples from related rates in section 3.7. I've got a handful of them here for the next one. You have to remind me how far we've gotten on these. 30. Okay, what are the questions? The second derivative? Yeah. I think I'm gonna do one word problem here.
Is it the web work that's due today or?
There you go. All right, let's work along here. Guys.
Yeah, which web work is this the one?
And 7, problem 8.
Oh,
Might have a different version. So, why don't we find the text? Equals.
No, once you get them on the board, they just don't work anymore. Here's a nice flat one. Right after a while, we'll solve that one. All right, everybody like that? Go through the equation and take the derivative of each term. Y is the dependent variable, so it gets the y prime term on it. Okay. Gotta move so I can see.
I'm sorry, you said this is, what word is this? This is the.
AO7,
And 7,
number
problem
8.
8.
Okay.
You lost the squares on the y, go in that dividing step. There you go. Okay, like that? Get the dy dx term by itself. All right, now we're ready to knock out the next derivative.
7.
Let's go ahead and label that as the second derivative. Okay. Got black hands in no time. Really, there's only one more step, and that's to substitute out the dy over dx. Okay, now, where will take that answer? Let's just make it more fun. Why don't you see how much simplifying you can do? Well, how about that for a good time? Okay, let me have a look at that. Everybody like that? So she canceled one of the y's, multiplied the two x's together. I'm happy with with that.
You can get rid of the light that you put in the title stuff. So,
Okay, so what did you do the next step?
So I did the same. like,
Multiply that by 3y, so you get negative 9y cubed, right?
Yeah.
Okay, what's next? When you multiply that by 3y, so you have a minus 6x squared. I think you're done. Got something you see you want to cancel. I think you're done, actually. 3 can come out anywhere. Or you can combine denominators.
You drop down,
Yeah, you can drop the 3y down with the other denominator.
it's gonna be 27 y.
That's pretty good. What do you think?
Yes.
I think there's a common factor of 3, but I'm happy with whatever you got right there. But like I said, it would have taken your answer way at the top of the middle column. I just think it might be easier to type in there unless the practice was good.
Oh, right.
Well, let's see. Let's see, type it in, see if it works. Very good.
What is AOC?
Right now, let's do this. Ready?
Oh. So,
I'm gonna keep whipping them out on you. There you go, free time, open up the web work, it's starting to count. Don't wait till it's due. It work? All right, so it's magic. If you work a problem on the board, you'll get it right. Anybody else want to do one? Scare everybody away now? That wasn't so bad though, was it? But if you want me to work a problem, I'll be glad to if you're a chicken. Anybody else have anything on web work?
Can I do AO6?
We can. Would you like to try it? You're good? You want me to try it? Son of a gun. Okay.
Man, you're making this such a work.
No, today was like Wednesday. Let's see, let me swap it to the next board. If you consider that east or west. It's not doing any. There it goes. There it goes. Okay, Assignment 6, I'm doing what?
That's number 15. So it's f of x equals 3x. And then 3x and then square root 4 minus 4x. And it's find the equation of the line tangent to the graph at x equals -2.
All right. So let's, while we've got f here, let's go ahead and get the y value. Let's put -2 in for each x to get the y value. So 3 times -2 gives me a -6 here. And then I have 4 plus 8. So I get -6 square root of 12. Okay, that'll work. Now we need the derivative. So I'm going to replace that square root sign with a 1/2 power. And how did you take the derivative?
Power rule.
And
I mean, not power rule, product rule.
product rule, but here we do power rule. All right, so let's do that. Product rule. First, times the derivative of the second plus the second times the derivative of the first. So I have 3x here.
I remember that.
Now we're going to bring the power down. Raise that to 1 power less. And then multiply by the derivative of what's inside. I get a -4 out of that. Then the other way, second. And then the derivative of the first is 3. Maybe it's easier if I write it in the front. Now we have to evaluate that when x is -2. So let me first write it with positive exponents. And I'm going to put together some of those terms that are hanging around outside. I'm going to take -4 and multiply it by half to give me a -2 times 3x to give me -6x. Then this other term is the one with the negative power, so let's put it underneath that with positive power. And then this other one we can leave alone. Now let's see if we can evaluate that when x is -2. I'll put a -2 here, and that gives me a +12. Down here, I'm going to get the square root of 12. And then in here, I'll get the square root of 12. We can put this together a little bit better if you rationalize the denominator here. What does this look like when you rationalize the denominator, this first term?
12 root 12 over 12.
So the 12s will cancel, and this is just root 12, right? So I got 1 square root of 12 plus 3 square root of 12 to give me a grand total of 4 square root of 12. So that's my y1. That's my m. There's my y1. And there's my x1. And so let's see if it fits right here. The equation of the tangent line is y minus y1 is m times x minus x1. So y minus the -6, so it gives me +6 square root of 12.
What was your x value? Your x1?
-2. And then I have 4 square root of 12, 12, and then x plus 2. So to type it in web work, you just move that over here on the end and it'll take it.
See, I think I messed up because I just plugged that equation in the calculator. And I
And you're
got
getting a
I got
decimal.
decimals, and I mean, I'm pretty sure I plugged it in right, so I would think that it would work, but I
Probably
guess
round off error,
probably. So
right? When WebWork wants an exact answer, it's not going to take round off, so.
and then I just have one more. It's,
Okay.
Number 10.
All right, anything else in boardroom here?
When you plugged in -2, did
Uh-huh.
you plug it into the original equation, obviously, to get y,
Right?
and then to get the slope, did you plug in x into the derivative?
Yep.
Okay.
Yep.
Okay.
Probably even simplify the square root of 12 over there. What's the
Right.
square root of 12 equal to?
2 square root.
2 square root of 3? You like square roots of 3 better than square roots of 12? Now to swap boards here.
Uh, 10.
Okay, which one am I doing?
Sequence. Number 10.
Okay, far away.
So it's let f of x equal x plus secant parentheses x to the third minus 7 parentheses. And this is all to the square root of -4. Sorry, yeah. Yes, ma'am.
All to the -4 power?
Yes, ma'am.
So you mind if I try to work it?
I'd love for you to work it.
And then, yeah, it's just fun first year. I remember this one. It's the seat, like the sequence that this one. Yeah, I had to like focus really hard to figure out which derivative goes on to what.
Like a little bit bigger. Just a little bit. It's hard to see on those screens.
That's true.
Power down. Leave all that alone. One more parentheses in there.
Oh, yeah.
Nope,
So-
nope. Swap places with your parentheses and your -5. We on the
Oh,
outside is the -5.
Right, right. So,
All right, good.
Since I see-
Now you're inside.
and then I think this is where like my parentheses can get messed up. So like, when I close the whole thing now?
Well, are you done with the whole thing now?
No,
You're still taking the derivative of that secant term, right?
correct. So it's
So
the
you
inside
keep
here.
the parentheses open and you know you're gonna knock out the derivative inside.
Okay.
Now you can close it. And that's kind of a big deal because that 3x squared only belongs to the secant tangent, not to the 1.
That belongs to just that.
Yes.
See, like I kept closing it and then
And that's the typical mistake that one would make.
See, okay.
So that 3x squared only belongs on the derivative of that second term.
What she gave us this problem. So we don't do that.
You can leave it there. There's really not much simplifying to do.
you can't apply the -4 to that.
No,
because
the the parentheses with the -5 keeps it that -4 out.
Okay, right.
So at best, you could put that power term on the bottom with a positive exponent,
Oh,
but we started with it with a negative exponent, so simplifying is not an issue.
all you really do is
That's
just move
really all.
that chart in front.
In front would probably make it prettier, but that's okay. Good, fantastic.
Thank you.
Thank you. So don't close your parentheses until you finish taking the derivative of the inside of the secant. So this is the derivative of the outside times the derivative of the inside.
I guess the reason I close it is because you take the derivative of like the first portion, which is the power rule, and then you close it, and then you do the next part, which is x plus secant parentheses, and then I finish that, and then I close the parentheses
But
and
you
I
didn't
open a new.
finish that. But you didn't finish that, right? Finishing it is going inside now and taking the derivative of the inside. Yes, sir. Assignment 7, number 7. All right, what does number 7 say? There. And you're supposed to find just the first derivative? Would you like to try it? Again, try to write a little bit big. You just didn't like that E to begin with, huh? Okay, so step back. She took the natural log of both sides. However, it'll work. Now keep going. Any reason for that move? Well, you're not gonna be able to get the y's together because this one's protected by a logarithm. So any more algebra that you do is kind of just a time waster. Why not just take a derivative from that line? Yeah. Like that. We could knock out a derivative. Use implicit differentiation. On the left-hand side, you can do the quotient rule. Whoa. What'd you just do? You need bottom times the derivative of the top. Bottom times the derivative of the top. Minus the top times the derivative of the bottom. Wait a minute, where's the top? So bottom times the derivative of the top minus the top. This is what you're missing. Times the derivative of the bottom. Bottom squared.
It's still.
There you go. There you go. Okay, step back for a minute so they can see that. So the bottom is y, the derivative of the top is 1. Then minus the top, which is x, the derivative of the bottom is the dy dx. All over the bottom squared. Okay, continue. Now you're going to go across the right-hand side, take the derivative of the log of stuff. Okay, so that's u prime over u. So the u was the 5x minus 6y, that's on the bottom. Then you go inside the parentheses, the derivative of 5x is 5. The derivative of 6y is the minus 6 dy dx. Okay, so step back for 1 minute. We're going to figure out how to solve that for dy dx. Boy, what a mess that is. We got a dy dx on the right. We got a dy dx on the left. We got all kinds of fractions. Cross multiply, and that'll get rid of the fractions. Want to try that? Come on up here, because the bottom of the board can't be seen on the video. Try to write a little bit bigger.
The left side looks like an optometrist test. What can you take the third to it? Now, if you don't need glasses, you can take the third to it. That's what it's like.
Okay, so multiply, let's see, y squared times that, 5x minus 6y times that. Okay, and maybe multiply it out, right? Because our dy dx's are stuck inside parentheses. We can't peel them out until we get rid of the parentheses. Now when everything's all spread out, it looks pretty good, doesn't it? So let's try to get the dy dx's on one side of the equal sign and the non-dy dx's on the other. Missing one, aren't you?
So just move all the.
Move all the dy dx's over. And she's factoring out the dy dx to save some ink right there. Now all the other guys are moving to the right. So let me underline them before you go on. She moved this one to the left by adding it, moved that one to the left by subtracting it. And then this one went to the right and joined the other two to the right. Now it's just a matter of dividing by what's in the parentheses. What do you think? Good? You guys watched all the signs and things like that. She didn't mess up any signs anywhere, did she? Question there somewhere?
I think the 6y.
We're keeping the 6y squared there, so it's still gonna be negative. And then we're gonna subtract 5y squared and there's the 6y squared. That's already there. That's already there. And that one's squished in the middle. Fantastic. Thank you. Yeah, here's the key. Let's see if it works. So this was a pretty clever step. I kind of like that. But you could have taken the derivative from here, right? The derivative of e to the u is e to the u times u prime. The quotient rule would have been that u prime term. Or you could have avoided the quotient rule and did the product rule here, but I don't know why. You can always rearrange your expression in the beginning to help you in the derivative step. You got more? All good then, huh? All right, then let's get out those examples and let's pick up where we were. We're doing the related rates equations. And so in our related rates problems, that's section 3.7. Okay, so yes, it said it was wrong. Okay, so let's check how you typed it in. Let's see. Let me see, you got 5xy. 5xy minus 5y squared minus 6y squared. Wonder why these are the same. Yeah, so you could make it minus 11y squared. All divided by maybe 6y squared. Minus 6xy plus 5. Okay, so something wrong. Let's figure out where. Okay, natural log of both sides. X over y. Natural log of that. Let's see the original problem. Make sure we talked down right. 6y. Okay. And then bottom times the derivative of the top is 1 minus the top times the derivative of the bottom over the bottom squared. Derivative inside is 5 minus 6y prime, 5x minus 6y. That's okay. Now I'm going to multiply y squared times that, y minus x dy dx times that. So then we have a 5y squared minus 6y squared dy dx. 5x times y minus 5x squared dy dx. Minus 6y squared plus 6xy dy dx. All right, I'm happy with that. Then we've got a minus 6y squared dy dx. Move that over, minus 6xy dy dx. Move that over, plus 5x squared. Good. That's already there. That's already there. Minus 5y squared. I don't know. I don't know. I don't know why it says it's wrong.
Sure.
Sure.
Good. Problem number
11. Good, good. Maybe it doesn't recognize that. Maybe it wants the answer from here. Let me try it from here without doing this log step and see how close we can get to that. So let's just start with this, and I'm going to take the derivative just as we see it, right? The derivative of e to the power is itself times the derivative of the exponent. So that should be some version of that. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And the derivative on the right-hand side is 5 minus 6 dy dx. With me to there? Okay. Let's see. If you want, we can get rid of the y squared and put it over there and just multiply out the top. So I'm going to multiply out the top and move the y squared over here. So when I multiply out the top, I have y e to the x over y minus x e to the x over y times our dy dx. And then over here, I have 5y squared minus 6y squared dy dx. And so I'm going to group terms. This one is coming over here. That one's going to go over there. I don't know what's wrong. Just didn't like your answer. So we do that to here. Minus x e to the x over y plus 6y squared times dy dx is equal to, that stays put. And that one moves over as a minus y e to the x over y. So our last step is to divide. Y over dx is that stuff. Divided by this stuff. Try that. It just doesn't recognize your answer is being equivalent to that. Pretty amazing that this program can recognize the answers anyway, right? Just think of all the different ways you can simplify this. That one works? So it just didn't recognize the answer without the E in it.
Is it possible that the 6y squared in the first answer was supposed to be positive?
Since I erased it, I don't know.
Here, talk about it later.
This one,
Yes.
this negative here, this is negative here, it's minus here because of that. I think that's okay. I mean, I kind of looked at the signs pretty carefully.
Somebody put it in Desmos and see if it's the same graph.
Yeah,
We don't have the same graph with Desmos. They don't have like the same whatever.
Oh, well. So maybe we lost part of the domain by taking logarithm. Wherever you take the logarithm, you're assuming that this is positive. Which one else do you think had a bad answer?
Probably 11, because that's 2 parts. And the second part is based on the first answer, and I got that one right. But then the first answer, it says it's wrong. But I'm like 99% sure it's right.
And you don't think there's any typos anywhere? All right, let's give it a shot.
It's at the right equals 4. Mark set to the 4x or 4x.
What are we supposed to do this?
Find the derivative.
Find the derivative. Okay. All right. So the derivative with respect to x of the arcsecant of u look like 1 over the absolute value of u times the square root of u squared minus 1 times u prime. So the 4 is a constant. Let me just put it on top. My u is 4x. And then 4x all squared is going to give me a 16x squared. And then the derivative of the 4x is going to give me yet another 4. So we get, one of those 4's can cancel here. So we get 4 divided by the absolute value of x times the square root of 16x squared minus 1. Is that the first part?
How do you type that?
Absolute value, there's a key on your, above one of your things is the straight
I think
law.
that's what I might have.
Sometimes it wants it, sometimes it doesn't. There you go. So like, this one does want the bars. And sometimes you can sneak away with it and sometimes you can't. We good?
You have to write that.
On this one you do. Didn't want it without. You can do ABS with parentheses, but there's a key that's got the absolute value bars. Right, there's a slash key and above it is the absolute value. Yeah. Good. Cool. Okay, let me go back to the other board. Yes, that all. Okay, now remember in the related rates problems, both x and y are functions of time. So we're taking the derivative with respect to t. We need to process the description of the problem so that in the problem, the things that are changing, we label with a variable. We write an equation that relates the variables at any time t. Take the derivative of that. That gives us our related rates equation. Then we go back and see if we have any numbers to put in and solve for whichever rate we're looking for. Okay. All right. So which one are we on here? 4.
You do this in physics.
Let's see. A 20-foot ladder leans against the building. If the bottom of the ladder slides away from the building at a rate, ding, 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 that's a derivative, of 2 feet per second, how fast, that's the other derivative, is the ladder sliding down the building when the top of the ladder is 12 feet above the ground? So let's draw a ladder leaning against the building. And 2 things in this picture are changing. The length of the ladder is not going to change. Look at that artwork right there. Am I in the wrong profession? All right, the ladder's going to stay at 20 feet, so I'm going to go ahead and label that at 20. The two things that are changing is that the bottom of the ladder is sliding away from the wall. The top of the ladder is sliding down the wall. So this length changes and that length changes. We're going to put variables there. So how about we use an X here and a Y there. Now we're given a rate of change. The bottom of the ladder slides away from the building at a rate of 2 feet per second. So that's a derivative. Which variable? X. That's the bottom of the ladder. dx dt is 2. How fast is the top coming down? So we're looking for dy dt. And we need it at a particular instant. And that's when the ladder is 12 feet above the ground. So the distance above the ground is the variable y.
So the dy would be 12.
No, dy is what we're looking for. Y is 12. 12 is feet. So that's not a feet per whatever. That's just feet. That's a particular measurement. Okay. So there's our problem. We're looking for dy dt, given those other pieces of information. Now what we need is some equation that relates x and y at any time t. What do you see out of the picture? The diagram theorem. So our basic equation that we're going to start with is x squared plus y squared is 20 squared. Now take the derivative with respect to t. The derivative of x squared is 2x dx dt. The derivative of y squared looks the same, but it has a dy dt. What about the derivative of the 20 squared? Now we're looking for dy dt. So we got to see if we've got numbers for everything else. We're going to solve for this guy here. Green's not going to work.
Use your imagination. So
Yeah.
it's like finding the equation.
Well, we can't think of that now as a tangent line thing. Now it's a rate of change with respect to time, not with respect to x. So let's see if we've got numbers everywhere. I'm going to put a 2 here, a 12 there. So we're going to need to find x. We need x at the instant when y is 12. So let's freeze frame the action and find x when y is 12. So we've got 20, 12, and x. 3, 4, 5 triangle. This is 3 times 4. This is 5 times 4. So what do you think that x has to be? 16. So that we have our 3, 4, 5 triangle. So x is going to be 16. Let's plug that in there. I'm going to go ahead and cancel the 2s. I'm going to divide everything by 2. So I have 16 times 2 plus 12 times dy dt is equal to 0. 16 times 2 is 32. I'm going to move it to the other side. Makes that a negative 32. And now divide by 12. Let's see, 4 goes into both of those. And that's going to be in feet per second. Does it make sense that it's negative? Sliding down the wall. So we're going to say the top of the ladder is sliding down. The wall at a rate of 8/3 feet per second. All right, so look how useful that is. You're here at the instant when that's 12 feet. Maybe you're 6 feet tall. How long before that ladder hits you on top of the head? How many seconds you got to get out of there? It's coming down at about, what, 2 2/3 feet per second? So at the end of 1 second, it's, let's see, 9 1/3 feet high. At the end of 2 seconds, let's see, 9 1/3 minus 2 2/3. You're about to get hit, right? You got 2 seconds to get the heck out of there.
But it's not assuming it's a consistent rate.
Right, it does depend on, it does speed up as it goes down while we meet that instant. You got 2 seconds to do that calculus and say, oh, I gotta get out of here. Okay, so in the first example, you were given an equation. In the second example, we were looking at the area of a circle. The third example, we did the volume of a sphere. This one we did, our governing equation was the Pythagorean theorem. Flip it over and you got some more. Swap boards here, so let me rub that out, then I'll put my camera. So while I erase the board, see if you can draw a picture. Identify what's changing with a variable. Identify what's given in terms of your variables and the rates of change. And then we'll figure out how to start. A boy 5 feet tall walks away from a street light at a rate of 4 feet per second. The light is 16 feet above ground level. How fast is the boy's shadow lengthening? Well, I need a street light and a 5 foot tall boy walking away from that. There's the ground. There's the street light. It is 16 feet above the ground. Somewhere over here is this boy. All right, let's make him look like a boy. He's gotten too tall though. He's only supposed to be 5 feet tall. All right, he's walking away. So he's walking like that. And he's got a shadow. This is projecting his shadow down here. So here's his shadow. That's also growing. And he's walking away at a rate of 4 feet per second. And we want to know how fast this is changing. So only where I have the arrows are things changing. The distance, the boy from the wall, and the length of his shadow. I'm going to stick variables right there.
If he's walking away from it, wouldn't it be shortened, not lengthened? Shadow?
I think it's going to lengthen. It shortens as he gets closer to the pole.
Oh, you're right.
I think he's going to get longer and longer shadow. Okay, so the two things are changing are the two arrows. So let me put an X is the distance of the boy from the wall, and the Y is the length of his shadow. And so this 4 feet per second is a dx dt. And dy dt is what we're looking for. Now we need some sort of equation that relates x to y at any time t. And we're not going to do a Pythagorean theorem because I have no information about the hypotenuse. Any other plans out there?
You do like sign or Andrew or
I
something?
don't have any angle descriptions either. So I don't have any angles related. Yes, I'm. Proportions, we have similar triangles. We've got the big triangle, and we've got the little triangle. In the big triangle, we've got 16:5. We know this. How long is this length in the big triangle? X plus Y. We're going to eventually take derivatives, so I want my variables on top. So I'm going to say this length is to that as this is to that, or I can say this is to that as this is to that. So I'd rather keep the numbers on the bottom. So using similar triangles, I'm going to say X plus Y is to 16 as Y is to 5. If you want to move the numbers, we can cross multiply. I can say 5x plus 5y is equal to 16y. Heck, you can even get the y's together. And now take the derivative of both sides. So you have 5 dx dt is equal to 11 dy dt. So it's the change in the length of the shadow doesn't even depend on how fast or where he is at any time t. It's definitely, it's all in terms of the rates. I know dx dt is 4, so I can put that in there now. I have 5 times 4 is 11 dy dt. And then divide by 11. So the shadow is growing, because that's positive, at a rate of 20/11 feet per second. So that was kind of a boring problem. The derivative is real, boom. Key was the similar triangles. Right, you try to relate what's given.
We're gonna have to come up with all of that, like on like the exam or something.
Well, sure,
Maybe that's
that's why
what
we're practicing them now. Back to the other board, and we'll swap my buttons here. So again, read the next problem. Draw a picture. Label what's changing with variables. And think about the equation that's going to relate those variables at any time t. Six. The balloon is rising vertically from a point on the ground, 200 meters from an observer on ground level. The angle of elevation between the observer and the balloon is increasing at a rate of pi/200 radians per second when the angle of elevation is pi/4. How fast is the balloon rising at this time? So we got a couple of things changing. The angle of elevation and the balloon going vertically. So let's draw the balloon rising vertically See if that fits on the screen. That doesn't fit on the screen. Here's the balloon. Rising vertically. 200 meters from an observer. That doesn't change at ground level. Here's the angle of elevation is measured from the horizontal to the balloon. That's changing. So let's put a variable here. We'll put a variable here. 200 doesn't change, so we keep that as a constant. So the angle of elevation, that's what I call theta, is increasing at a rate. That's a derivative. D theta dt is pi over 200. That's at the instant when theta is pi over 4. So the key that this was a rate is that it's given in radians per second. And this is just radians, so that's a fixed measurement. We want to know how fast the balloon is rising. We want to be able to find dy dt. Doesn't show the bottom there. So I need some sort of equation that relates theta to y. Tangent, I got the opposite and I got the adjacent, right? Tangent of theta is opposite over adjacent. That's the equation that we're going to start with. Now let's take the derivative of both sides. Derivative of tangent is secant squared theta times or d theta dt. I don't need to use a quotient rule on the other side because the 200 is a constant. I can pull 1 over 200 out and now take the derivative of the y, and that's our dy dt. Now let's put our numbers in. Theta is pi over 4. D theta dt is pi over 200. Dy dt is what we're looking for. So we've got numbers for everything. Let's put them all in. I need to know the secant squared of pi over 4. Then take that number and multiply it by pi over 200. And then solve this equation for dy dt. So, what is the secant of pi over 4? Or do you know the cosine of pi over 4? Okay.
Which means it's just going to be your 2%.
When I rationalize, it's just going to be square root of 2 for secant. Right? Now I got secant squared. So I got square root of 2 squared times pi over 200. It's equal to 1 over 200 here, dy dt. The 200s will cancel if I multiply both sides by 200. So we're done. 2 pi is dy dt. Yeah, just give me an equal. So in words, y was the balloon. So the balloon is rising positive at a rate of 2 pi. What would that be measured in? Meters
Oh,
per
that's how you-
second, because it's a rate. Okay? A little over 6 feet per second, that thing's going up.
the 200s cancel because you just.
Multiply both sides by 200. All right, let's see. You like that? This one we use a little right triangle trigonometry to get our governing equation. So same deal. Let's read the next one. You guys draw a picture. A water tank has the shape of an inverted right circular cone. So when you read that, that means the point is down. Inverted right circular cone. Altitude 12 feet, base radius of 6 feet. Water's being pumped into the tank at a rate of 10 gallons per minute. Find the rate at which the water level is rising when it is 3 feet deep. Use 1 gallon is 0.134 cubic feet. Picture here. Oh. Altitude is 12 feet. Base radius is 6 feet. Water is being pumped into the tank at a rate of 10 gallons per minute. Find the rate at which the water level is rising. That's this. Find the rate at which that is rising when that measurement is 3 feet.
Is that one-third r squared h? Is it like
What is it that you're, what formula are you pulling out?
volume?
If a gallon is 0.134 cubic feet, what kind of thing is measured in cubic units? Volume. So we're looking for the volume of the cone, right? So this is going to be a rate of change in the volume. So if 1 gallon is that, then 10 gallons is going to be 1.34 cubic feet per minute. So put those two together, and that says the volume increases at a rate of 1.34 cubic feet per minute. The other thing that's changing is the height of the water. So let's call that, what do you want to call this? New variable. H. So we are looking for dH dt at the instant when H is 3. So this is the volume of the water. That's the height of the water. So we're going to use the volume of a right circular cone. Did I give that to you? I did not.
That's what I want to say.
All right, what did you tell me it was?
I think it's a one-third of a, whatever it's called.
1/3 of a cylinder, right? Pi r squared,
H.
r squared, or pi squared, r squared h. Everything with a point has a 1/3 in it. And then the pi r squared is the area of the circular base, and then the height is the height of the liquid. All right.
So, that's what I was asking earlier. Are you gonna provide us with those like formulas or?
Oh, yeah. Oh, yeah.
Okay.
Maybe you'll know them by then. As h grows, so does r. R is this r, the radius of the water. But I have no information about that. So I want to see if I can get the r out of there. Because r is changing. As that water gets deeper, r is getting bigger. So it changes, h changes, but I have no information about how it changes. So my problem is I don't want to take the derivative from here because I don't want to have 3 variables that change with respect to time. I only want to have 2 of them that change with respect to time. So is there a way to substitute the R out of here?
You can get R with respect to B.
R with respect to V,
Or, I don't know.
I can get R with respect to H. I've got
You
the
already have R.
water that's shaped like a cone, and then I've got the cone that's shaped like a cone. So they should be moving in proportion to each other, right? The water has the shape of the cone is the shape of the cone, but they'll always be proportional. So I've got similar triangles again. I've got the 12 and the 6, and then I've got the H and the R. So 6 is to 12 as R is to H. 6 is to 12 as R is to H.
Wow, that's.
So throughout this whole thing, R behaves like 1/2 of H. So I'm going to go back and rewrite this formula without the R. Put in 1/2 H where the R is.
Why is it 6/12 of R over H?
Radius is to height as radius is to height. Similar triangles. Dimensions of the liquid, dimensions of the cone.
I guess I was wondering like why
What do you mean?
like why it's 6/12. It's just like-
Radius is to height as radius is to height. Similar triangles. Radius of the cone is the height of the cone, as radius of the water is height of the water. Just like the similar triangles we used in the last example. So now I have my equation in terms of the 2 things that are changing. I'll take the derivative of it, but I'd rather simplify it first. If I square that stuff, I'm going to get a 1/4 times the 1/3 is going to give me a 1/12 pi. And then I'll have an H cubed. Now take the derivative of both sides. On the left, we get dv dt. The 1/12 pi is a constant. Pull it out. Take the derivative of H cubed. What will you get as that derivative? Now let's put our numbers in as we simplify. We're looking for dH dt. 3/12 is 1/4. dV dt was that funny number, 1.34. Then I said this is going to become 1/4 pi. H is going to be 3, so this is 3 squared. dH dt. So this becomes 9 pi over 4. I want to get it over here. And so I'll just divide by 9 pi over 4. And when I divide by 9 pi over 4, I have the 1.34. I'll just put divide by 9 pi over 4. And I multiply by 4 and then divide by 9 pi. I don't want to mess with the numbers. Let's just say that is going to be in, let's see, that was measured in 3 what, feet per minute. It's the rate at which the water level is rising. See if we can at least get the next one set up in the remaining 5 minutes. West. All right, a block of ice in the shape of a cube, originally having a volume of 1,000 cubic centimeters, is melting in such a way that the length of each of its edges is decreasing at a rate of 2 centimeters per hour. So all that was describing volume. At what rate is the surface area changing at the time that its volume is 64 cubic centimeters, assuming the block of ice maintains its cubical shape?
Just ask it in a nice and maintain the cubical shape.
The fact that it's a cube means every dimension has the same length. So I can just use a single variable here. Those are changing. As those change, volume changes and surface area changes. So I need an equation for each of those.
6x squared x cubed.
Okay, so volume is x cubed. Surface area is the sum of the areas of each of the faces. Each face is a square, and there are 6 faces. So surface area, I'll just write as area, 6x squared. Okay, so I don't know that we need the 1,000 cubic centimeters. Let's hold on to that for a minute. The length of each of its edges is decreasing at a rate of 2 centimeters per hour. How do I label that 2 centimeters per hour? That's a linear measurement. That's a dx dt. At what rate is the surface area changing when its volume is 64?
The 2D maybe.
Yeah, it's decreasing. Okay, blah, 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 blah. What rate is the surface area changing when its volume is 64? I don't know where we'd need that. But if we're asked to find this, I bet we take the derivative of that. So let's do it. dA dt is 12x dx dt. You see now why we need that? I don't have a value of x. So we want to know it at that instant. Let's find the value of x at that instant. So we need this when volume is 64.
So what's the 1,000?
Nothing. So we have 64 is x cubed. What number do you cube to get 64? 4.
So.
Now we can fill everything in. dAdt is what we're looking for. So I have 12 times 4 times the negative 2 because it's decreasing. So 8 times 12, is that 96? And that's area, so that's going to be centimeters squared per hour. So the area is decreasing at a rate of 96 centimeters per hour. Okay? Centimeters squared per hour. We did it. We finished related rates. Next time we'll talk about something called the differential. That's the differential. All good? All right. Get busy on that web work. And
Apologize for missing classes.
make good money for this class. Okay. All right, log on out of here.
Alright, so like we touched the topics and things, so I'll be taking the medicine here.
Okay.
For the days I take it, like, I probably won't be on color class that day. or
Okay.
The day after,
Okay,
so I might have to do this.
that's fine. I'm recording, or if you feel up to watching it live, it'll be,
Because like they told me, like, I may not feel good after, so no point coming to like.
okay, yeah. Oh, I'm sorry to hear that. Okay,
I mean, I'm probably fine, but just like in case.
Right,
I don't
right.
want to-
okay, I'll keep recording.
Thank you.